So, we see that this is a representation of the structure drawn by a program. This is a program called Pluton. There are several programs which can do this Hortep plot, and this is the structure of sucrose. So, the sucrose structure is determined, and then its positions of the atoms, the carbon atoms and oxygen atoms are shown, and so on. I was talking about the hydrogen positions. So, in a situation like this, there are two ways in which hydrogen positions can be determined. One is to put all the atoms in their final positions, as we have done the refinement, and once we have those in the final positions, do a F calculated. That is, you go back to this calculation and then do a F ops minus F calc. So, all the atoms are in their final accurate positions, and so you got a difference of F ops minus F calc. So, that will be now the representation of whatever is left out, which is reserved for hydrogen atom positions. Or for that matter, if you have an atom which is wrongly put or wrongly introduced in this process, then it will also start showing up when you do a delta F based Fourier map. So, in the Fourier map, now you do not use F ops, you use delta F. So, when you calculate the Fourier map, you use delta F, and that means you will use the whatever is the electron density that is left out, and that is known as a difference Fourier plot, because we are taking the difference of the Fourier values of the observed and the calculated. So, therefore, it is a difference Fourier plot. So, when we do this difference Fourier plot, the hydrogen atoms, many of them will show up as possible small density values, around 1 electron per angstrom cube, and these positions therefore can be fixed now. We can identify their hydrogen positions, and then we see also the geometry that is associated with those hydrogen positions. In case it is not coming out clearly, the hydrogen positions, then one can use the stereochemical information that is available in the molecule. In case of sucrose, we know whether it is up or down, whichever way the hydrogen positions are going. We call them alpha and beta in the sucrose nomenclature. So, those hydrogen positions therefore can be actually fixed at that particular distance and angle which it is making with respect to the atoms. For example, this hydrogen atom which is coming out of this carbon atom, the oxygen atom is going down. So, the stereochemistry around this particular carbon is tetrahedral. So, we have now the 3 directions fixed. The 4th direction can be now given to the hydrogen atom, and at the corresponding distance, which is normally a normal OH distance is about 1 angstrom. So, we take 1 angstrom from there and fix the hydrogen position. So, then we do not touch the hydrogen position, but we allow the carbon, oxygen and other surrounding atoms to refine. So, whenever the new positions of these carbon comes up, this hydrogen automatically is fixed again at 1 angstrom. That means this is referred to as a riding hydrogen. So, we call this as a riding hydrogen because it rides along with this atom. So, whatever happens to this particular atom, hydrogen in any case will not leave. This is like a rider sitting on a horse. So, as the horse keeps moving, he is not going to be displaced, he is stuck to the back of the horse. So, the hydrogen therefore is riding on the corresponding atom to which it is attached. So, this is known as the riding atom hydrogen atom refinement, in which case the distance is not altered. The hydrogen atom position is therefore now depends upon how the positions of the other atoms nearby change. The other thing which we can do, of course, is once we have the difference Fourier hydrogen identified, and if we still have a good data at our disposal, then we can try refining the hydrogen positions as well, but refine them with respect to the isotropic value. So, that is why you see only circles here rather than ellipsoids, because this is now associated with what we call as an isotropic thermal parameter. Only one thermal parameter is associated with respect to x, y, z, and since there is only one thermal parameter, you will have a circle instead of a ellipsoid. So, these hydrogen atoms therefore are represented by circles, and this is now a full representation of the particular molecule. So, this is how we get the molecule in the asymmetric unit represented in a diagram like this. So, just to recapitulate, we got into a situation where we had the initial electron density map of some kind, and this particular initial electron density map could give us some atoms in the structure. We took those atoms to be the correct atoms, calculated the structure factors from the electron density associated with these atoms. That give us the calculated structure factors. The calculated structure factors and the observed structure factors are subtracted from each other, and the corresponding agreement factor or the reliability index R is calculated. And this particular R value should be going down as we improve the f ops minus f calc. If we find that this f of minus f calc after the so called re-evaluation goes and makes the R factor higher, that means either the atoms are in wrong positions, or some of the atoms are in wrong positions, some of them in the right positions, and all these will be revealed in the difference Fourier map. So, if we do a difference Fourier map, it will come with ups and downs. We will study a little bit of how these Fourier maps come up in terms of a numerical example, so that it makes life easier. We will understand how the associated electron density features come up by taking an example of a Fourier series and checking out how we calculate the Fourier series when we do the difference Fourier plot. So, in this particular case, we do a difference Fourier plot and try to improve the condition. Right. So, as and when these things are all done, this is referred to as the refinement of the structural model protocol. We now refine the hydrogen atoms or riding on their carrier atoms as we just discussed, and therefore, we have now completed the refinement of the structural model. We go ahead and calculate the so called R factor. These R factors will not go towards 0, they go towards 0, but they will not be 0, because that would mean f ops and f calculated are exactly equal to each other, which will never happen due to uncertainties involved. We have so many uncertainties involved, like for example, determining the thermal parameters, there are uncertainties. Determining the position of xyz, also there are uncertainties. The thermal ellipsoid feature will not allow the R factor to go towards 0, because we cannot pinpoint the exact position of xyz. The only thing that will happen is R factors will go lower if you collect the data at lower temperatures. If you collect the data at higher temperatures, then the R factors will not go down. It will have a certain value at which it will sort of remain the same. So, then such situations we call it as convergence. So, we go and find out the optimal value of R, and when we reach the optimal value of R, we say that we have reached convergence in the refinement protocol. Now, let us see, after having done the structure and having got a good R factor and successfully determined the structure in the space group which we have determined, and based on symmetry, we have now the structure information. So, once we have the structure information, how do we analyze the geometry and intermolecular interactions? This is the next step which we will take up, and in this particular step we see that we have to determine the geometry of the way in which the atoms are arranged inside the structure. So, that means we need to find out bond distances, bond angles, torsion angles, ring puckering geometry. In the case of sucrose, you see that we have the puckering of the ring, etc. So, all the molecular properties can be calculated here. In case there is an inorganic system, we can calculate the coordination distances and so on with respect to the inorganic atom which is present there. In case of organic metallic samples, we can also calculate the way in which the coordination sphere develops around the metal atom. We can also calculate, because of the fact that we have not just one molecule in the unit cell, more than one molecule in the unit cell, we can now construct the rest of the molecules in the unit cell. So, what we have determined by the structure determination is only the asymmetric unit atoms. So, we can now take the asymmetric unit atoms, use the symmetry information which we have in terms of both structure and symmetry, in terms of both space groups and symmetry, and then we can then calculate the contacts between molecules. This now refers to the interatomic contacts. So, we can determine the intermolecular contacts, and the interatomic contacts are available here with the bond distances, angles and so on. So, the complete geometry associated with this can be calculated using programs like Platon, PAST, etc. These are all ready-made programs, downloadable free of cost. After that, we have to see there are no funny contacts. So, suppose now you solve this structure and then the structure develops some contacts which are very much shorter between intermolecular contacts, then you know something is wrong. So, anything wrong at this stage of the geometrical calculation one can find out and redetermine the structure. So, this is a place where the reliability of the structure determination is evaluated. Having got the geometry and the intermolecular interactions evaluated, we have to actually now validate the structure. The validation of the structure is done according to the International Union of Crystallography rules. See, everything is under control of the International Union of Crystallography as far as structure determination and structure reporting is concerned. So, the refinement results, all the results which we have got, they are referred to as a crystallographic information file. So, this is referred to as the file CIF. So, one has to have a CIF file available for any structure that is determined, and that CIF file will have so many factors. CIF file will consist of the ABC alpha beta gamma, the standard deviation that is in the ABC alpha beta gamma, the coordinates x, y, z and the 6 thermal parameters if it is anisotropic refinement, the hydrogen positions and their isotropic or anisotropic parameters. All these features will be reported under the CIF file, along with the fact that the CIF file will also contains information about the nature of intermolecular interactions in terms of how they are bonded to each other. What is the symmetry operation which takes this molecule 1 to molecule 2 through a hydrogen bonded interaction, for example. All such things are reported in the CIF file. So, once CIF file is available, one can calculate all the geometry that is associated with the structure. Then we also put the structure validation is also seen in terms of the FOPS calculated data, that is the final values of the observed and the calculated data, and this is known as a FCF file. So, together CIF file and FCF file now represent the geometry and the structure information together, because once we have an FCF file, it is possible to calculate the electron density map directly and then verify for yourself that the structure is what is reported in the literature. So, the CIF value and the FCF values are all available once the structure is made, and the structure validation is checked under the IUCR protocol, which uses what is known as a check CIF tool. There is also what is known as a Platon validation tool, which checks on other aspects, including the aspects associated with intermolecular interactions. It will check the various ways in which one can identify the hydrogen bonds, the halogen bonds and other kinds of bonds. We will not, it is not necessary for us to go into those details because it does not come under the purview of the syllabus of this course. But that particular course could be a course on advanced crystallography and the information we get from crystal structures. We can also check in the Cambridge Crystal Structure Database, which houses all possible structures determined so far, all the CIF files, all the FCF files which are now available for all the structures determined from day 1. So, the entry is crossing 150,000 entries so far, and it adds every day some 15 to 20 structures additionally. So, then we can check the similarity between structures by using the Cambridge Structural Database. This will bring us to the issue of how we do crystal engineering analysis. I will have some time towards the end of the course to discuss about that. So, we can also look at hydrogen bonds, various types of hydrogen bonds, strength of hydrogen bonds. We can calculate the energies that are associated with it separately. So, essentially the structure once determined has to be validated before it is put into circulation. Before it is published, one has to look at the CIF value and the FCF file format values in order to make sure that they go through the officially approved check CIF protocol. If check CIF says there are no errors, then your structure seems to be in order. Okay. There are certain problems which you will face. Any experiment will have problems. One is of course the way in which your diffractometer is set up, the laboratory conditions and all that. Considering all that deficiencies being overcome and you have a perfect system on which you can do a good data, the first major hurdle is the crystal quality. So, this is particularly so in the case of macromolecules, where the crystals of proteins and other complexes cannot be so easily grown. It is mainly because of the nature in which they fold themselves and the nature in which the interactions are coming in. So, the poor crystal quality can also occur in very, very small crystals as well. So, for example, if you get fine needle bundles all together, that will not give a good diffraction. So, that is the poor crystal quality. So, this is one of the technical problems one would come across, and when we collect data on a very poor quality crystal, it may be misleading and it may not give us the structure which is the correct structure. The second one, as we always been stressing, determination of the correct space group symmetry. Now, if we have a wrong space group symmetry identified, then the structure determination will run into serious technical problems. There is an issue of what is known as a pseudo symmetry, and this issue of pseudo symmetry can come up with respect to the molecule. It can also come up with respect to the space group that is determined. So, this anomaly is going to put us into some serious issues. I do not think I will have necessary time to cover the details of this, but this is a warning place where we can also have this pseudo symmetry as a technical problem, since I am just listing out the technical problems. Absolute structure of light atom structures is a question mark. We use the FLAC parameter or whatever, but essentially we make use of the fact that there is anomalous scattering effects, but the anomalous scattering effects at a given wavelength, like for that of copper or molybdenum, they are so small for lighter atoms that the determination of the absolute structure is a questionable entity. If you do have a very heavy atom, then the value of the anomalous features will be higher, and then the absolute structure determination is reasonably accurate. So, this is another technical issue which will come up. The more complicated technical issue which comes up is the so called twinning. So, some of the crystals, just like we have in humans twinning problems, we also have twinning problems in crystals. Crystals can grow as twins, and there are lots of different kinds of twins that can grow. Some crystals grow as merohedral twins, that some crystals grow with a one axis unique, but they grow together. All these problems will cause the nature of the diffraction then will be different, because diffraction will be coming from both these crystals, and those two crystals are joined to one another in some fashion. Unless we know in what fashion they are joined to one another, we will not be able to understand and appreciate the analysis of the data which comes from that. So, twinning is not a virtue, it is a curse, is a technical problem. Then there is also another issue which will bother in many cases, and this is a very serious issue particularly for pharmaceutical compounds: positional and substitutional disorder or part or even the whole molecule. Sometimes the whole molecule is disordered, that means it is not in one position, it can be in two possible positions. The symmetry will allow it. The problem is the symmetry that is associated with the determined space group will allow for the positional and substitutional disorder, and this therefore will give rise to different kinds of diffraction conditions. It may look as though because of this positional and substitution disorder, the molecule is going into two different crystal systems, which is the definition of polymorphism, but it is not the case. It is essentially the possibility of positional and substitutional disorder of the molecule. The other technical problem we normally face, particularly in larger molecules, is the disordered solvent. So, the solvent may be fully disordered or partially disordered, because most of the protein crystals crystallize along with the solvent water, and this solvent water has no structure of its own, it is disordered, and because of that we will get what is known as diffuse scattering. So, apart from your single crystal diffraction which is coming out from the system, you will also have diffuse scattered radiation coming out of this disordered solvent, and as a result the actual evaluation of individual reflections coming from the crystal system becomes an issue, and it is not going to be very easy. There is another thing called the incommensurate structures, that is this is possible because the way in which sometimes the crystals grow, the cell dimensions which we get will be not sufficient to describe the orientation of the molecules in different unit cells. That means the molecules now can orient, they have to be exactly the same in the next unit cell, that is the definition. by translational periodicity, whatever molecule we are getting in a crystal structure in the unit cell should repeat itself in the next unit cell, should repeat exactly the same way in the third unit cell. It may so happen that the second, third and fourth unit cells, the molecules are slightly rotated from each other. So, it is not an exact replica of the first unit cell. The exact replica of the first unit cell, let us say, comes at the fourth unit cell. Then we call it as the commensurate modulation. So, the unit cell now, cell dimension now is not the one unit cell, it is that of the fourth unit cell. So, we have to go from first unit cell to the fourth unit cell, fourth unit to the eighth unit cell and so on, and that is now the repeat distance. This is a technical issue which can be sorted out. On the other hand, if it is not repeating exactly at 4 unit cells, but somewhere around 3.5, then it is called incommensurate structure. There are what are called incommensurate waves which go through the crystal, and one has to determine that. So, these are all technical issues which will create problems. For example, we will get diffuse scattering, we can get streaks and diffuse layers of reflections and so on, and these reflections can also cause serious problems. So, since we face these technical problems associated with crystals, one has to be aware of these pitfalls, and these pitfalls might also create bad data. And once we have a very bad data set, the structure determination is going to be difficult. So, whenever we grow a crystal, we should look at all these possibilities, and if such possibilities do exist, we have to get rid of them or regrow the crystals such that we get rid of all these. There are certain issues which we cannot get rid of, like twinning we cannot get rid of, like incommensurate modulation we cannot get rid of. The presence of disorder and disordered solvents we cannot get rid of. So, one has to be aware of these and see how we can account for these technical problems, how we overcome, or is there any way in which we can solve these problems. Some of the problems which can be solved are, for example, we can solve the twinning problem, we can solve the incommensurate structure problem. The substitutional disorder, positional disorder part we can evaluate, but we cannot solve it. It can still be a part and parcel of the structure which has been determined. The disordered solvent, of course, will remain disordered, and so also the diffuse scattering streaks, diffuse layers and so on. So, these are all part and parcel of any experimental protocol, and experiments do have these kind of difficulties. So, what I therefore want to say is that I will go back in a few slides and then tell you what we have done with respect to the data collection. So, when we put a crystal and collect the data, we get these reciprocal spots. These reciprocal spots now can be indexed, and we determine the all possible HKL values from which we get the unit cell dimensions. And once we have the unit cell dimensions, we can use this 1 by d square HKL formula to determine the crystal system based on these, and therefore get the ABC alpha beta gamma values. And then we determine the space group by looking at the systematic absences in the structure. We can also get the cell dimensions, and then of course Laue symmetry is there already, and the analysis of the intensity statistics, which will tell you the difference between centrosymmetric and non-centric systems, will also be possible to use this methodology to determine the crystal system, whether it is a centrosymmetric or a non-centric system, particularly in cases where systematic absences are not helping. And then we of course go to the structure determination. We follow this protocol, determine the electron density, get the starting model. The starting model is now put back into this calculation, and therefore we solve the phase. This is the major problem, the phase problem. So, we get only the estimate of the phases. So, we get the starting model. The starting model electron density is analyzed, atom positions are identified, and the F calculated is made with respect to that. Then we take the difference between the F observed and the F calculated, and that delta F analysis will give us the rest of the atoms. We go through this protocol until we do not get any more of better value of the so called R factor, and at that stage we will now this is the set of refinement procedures which we will follow, and that is where we stop and say refinement is complete, and make a representation of that in an RTEP plot. So that is the overall protocol, and then of course we analyze the geometry. The structure validation of course is very crucial, and this is the overall experimental procedure. Now, having seen the overall experimental procedure and the technical problems that are involved, we will now go into the details of how we take the data, how we treat the data, and how do we reduce the data onto an absolute scale before we subject it for structure determination protocol. And this is the one which follows here. Well, we have already learned some of these things, but I will go through it in such a way that we get a hang of what we have to do. This is again an experimental data. So, experimental data will give us the intensity measurements. We have of course HKL identified. So, the modulus of structure factor is proportional to root of I. So, it is used in the calculation of the electron density map. This is, I have written it again just for your continued remembrance and also as a continuity. I will not be explaining it again and again because you know what we have written here. So, we convert the intensities into observed structure amplitudes modulus of F naught by a data reduction program. Now, this is where I told you that we can collect the data on any part of the surface of the earth on any instrument. Maybe we can even collect data in space, it does not matter, but what instrument you are using is deciding what intensities you will get, because it depends upon the input radiation, the scattered radiation, the efficiency of the detector and so on. So, once you have that data, you have only a relative data, relative intensities. Therefore, you get a modulus of F which we call as the observed structure amplitude. Now, we have to treat this data or what we call as a data reduction methodology such that we correct for all systematic errors that might occur on this particular value. And one of the rigorous procedures which must be followed before we go any further is to treat this F of HKL by this expression. The expression tells us that the F of HKL modulus, of course, it is I HKL to the power of half as is shown here, and that proportionality constant is replaced by K by LP, capital K by LP, capital L and small p. Now, the quantity P is called the polarization factor and the quantity L is called the Lorentz factor. The polarization factor depends upon the incoming radiation and the scattered radiation and is a simple function of 2 theta. So, we can correct this P as equal to 1 plus cos squared 2 theta divided by 2. So, independent of the method used for data collection, except when a crystal monochromator is used, we will not go into the detail of it, except to tell that this polarization comes up as a fact is due to the fact that when the X-ray radiation is coming, they are all circularly polarized. That means the electromagnetic waves are uniformly oscillating in all directions, and when they impinge on the diffracting plane or the reflecting plane, on reflection it so happens that they go in such a way that they are partially polarized. So, when we measure the intensities, we are measuring the intensities of partially polarized light, and P is the factor which corrects for that partial polarization. The factor L depends upon the way in which we measure the data. Remember, we have this problem of the reciprocal lattice rotating with the crystal, and the origin of the crystal is somewhere at, let us say, some central point, and as you go in the reciprocal space to higher and higher angles, the amount of time that is spent by a reflecting geometry sphere, that means you have the way in which the diffraction occurs is that that particular point will intersect with the Ewald sphere. Whenever the reciprocal lattice point intersects with the Ewald sphere, then we get diffraction. Now, the amount of time that is spent by that particular diffracting point will be different depending upon the orientation and the distance of that point with respect to the origin, and this is where we have a issue. So, the issue is in terms of L, which is called the Lorentz factor, and this is measured dependent upon 1 divided by sin theta. So, we use this L and P. This is independent of the method of data collection we have used, it is independent of the instrument we have used. The LP is a constant factor. So, we calculate this L into P and put it in this expression. K is the overall scale factor with which we have to now put the f of HKL on and take the I of HKL, take the square root, and K is the proportionality constant. LP correction is made on the every intensity which we observe. So, the values of L and P are listed in international tables again in a different volume, not in the volume where we find the space group information, but in the second volume of the international table. So, one can get the values of L and P. As you see, they depend only on the scattering angle, and therefore, since they depend on the scattering angle, they depend upon at what angle the scattering is coming, at what angle the HKL reflection is coming rather than anything else. So, therefore, it is possible to get the LP corrections uniformly organized for every given wavelength. It is going to depend on the wavelength obviously. So, it is a wavelength dependent correction LP, but it is available on the international tables. Now, K is depends on the crystal size, the beam intensity, and the number of fundamental constant. It is normally a constant for a given set. That is the proportionality K we are talking about here, depends upon the way in which we collect the data. So, effectively we have to treat the intensities and make the corrections associated with the Lorentz and polarization factors before we process it further. This whole processing of the data depends upon various issues. It also depends upon the way in which the amount of X-ray gets absorbed inside the crystal, and the way in which the total internal reflections can take place depending on what we call as extinction factor and so on. These are all parameters, these are all factors which affect the diffraction condition, and these factors which affect the diffraction conditions obviously are parameters. So, we can refine these parameters overall in our structure determination protocol. So, the absorption correction can be applied, we can refine the absorption correction in the way in which we would like to do, and also the case of the extinction, we can apply the extinction correction. So, therefore, the data has to be manufactured in such a way that this particular data which we are going to use finally is put on an absolute scale. So, in order to put that data on an absolute scale, we have a protocol, and that protocol we will have to depend upon the fact that we have already made the structure factors into a proper position and a proper scaling. So, the amount of information which we have is enormous. We have a very large number of data points, and those data points now has been treated for this data reduction protocol. So, we now have a collection of f of HKL. This f of HKL is now devoid of all systematic errors as far as possible. The only problem is it is still dependent upon the way in which you have collected the data, the instrument that is used, the way in which the detector has been placed. So, it depends whether you have used a photographic film, or you have used an imaging plate, or you have used a CCD detector or a CMOS detector. So, it all depends upon the power with which you can convert the number of photons which are falling on the detector to the electrical signals which eventually measures the intensity. So, the intensity measurement therefore is a totally relative phenomenon, and so we have to therefore put this intensity measured on an absolute scale, and the measured intensity to be put on an absolute scale essentially comes from the fact that we need to have them on the scale which counts the total number of electrons. So, what the logic of this whole thing is that we have a crystal, and in the crystal we have electron density, and the electrons are all over the place, it is distributed all over the place. Of course, they are atom centered, but anyway for all practical purposes it is not the position of the atom which matters now as far as the scattering overall is concerned. It essentially matters that we have the total number of electrons. So, what we can do is we can normalize all the structure factors with respect to the total number of electrons. So, in other words, the quantity F00, which is our standard quantity. So, the quantity F000 is equal to the total number of electrons. So, we can call it sum over all the Z values of every atom. So, if you have I atoms in the structure I1 to n, so sum over Z of I. So, suppose you have 20 carbons, 30 oxygens and so on. So, 20 times 6 plus 30 oxygens times 8, that summation will be now the F of 0, 0, 0. So, that gives us the overall content of the unit cell. So, the overall content of the unit cell is sum over Z of I, which we have to determine. This includes the symmetry related atoms as well. So, that provides us the required scaling, and that required scaling is the one which we will have to worry about. And how do we find that scaling factor is something which we will discuss in the next class.